Okay, topic of power. So, what is power? Power is the rate of energy transfer. Now that actually tells us quite a lot right there. It will have units of joules per second. Energy per second. It's a rate of energy flow. We call joules per second a watt, W-A-T-T. Capital W is its symbol. Okay, that does mean if we really split things down and went to split hairs, 1 watt equals 1 joule per second equals 1 Newton meter, Newton times meter per second, is equal to 1 kilogram meter squared per second cubed. Mathematically, how do we define it? Well, the power, capital P, is equal to the rate of energy transfer, so we can use delta E over delta T. That gives average power. Or if we want instantaneous power, that is just the derivative of the energy with respect to time. Now, I'm going to add to this. Power average is the change in energy over the change in time. You can also write that as the change in work over the change in time, because the change in energy of the system depends on the work done on the system from outside. We can also then write that the power is the derivative of the work with respect to time. Okay, so that's some simple definition-y stuff. There is another equation that's interesting to us. So as a reminder, in a lot of cases we can write the work as the force times the displacement, delta R. And in cases where we can do that, if the force is constant, then if we take the derivative of the work with respect to time, we'll get the force out in front, and we'll have the derivative of the position with respect to time. In other words, we can actually write this as force dot product the velocity vector. And that is our final way of writing power. That one is not always relevant. The first two ways of writing it, just as the derivative of work with respect to time or energy with respect to time, or for the average, writing it as the change in energy with respect to time or the change in work with respect to time. The first two are the more fundamental ones. The third one we can sometimes use, but not always. Okay, how is power different from energy? Like, give it to me. How can we tell which is which? Well, here's a fun thing to think about. If I walked up steps and went from one floor to another, as I'd mentioned in the first introduction video, that would be somewhere on the order of 2,500 joules of work. Now, as long as I do it at constant speed, there's no change in kinetic energy, so I'm not doing additional work to speed myself up or slow myself down. So I can walk up those stairs at constant speed, or I can run up those stairs at constant speed, or you can. And think about this. Which one makes you feel it more? Which one makes you tired faster? And the answer is actually pretty obvious. It's harder to run up the stairs than it is to walk up the stairs. And it's not just a matter of the speed being higher, because we're not really changing our kinetic energy in the process. So, an interesting thing to point out. Work depends on the distance but not the time. So work to climb stairs is constant. But the power changes in the two cases. If you run up the stairs, the time is shorter. As a consequence, consequently, the power will be much higher if you run up the stairs. And that's actually why you feel tired when you try and do exercise, because you're moving at a much more, well, you're expending the energy at a much more rapid rate. It's not just that your kinetic energy is higher, because it actually doesn't take that much kinetic energy really to accelerate you up to like walking speed or even jogging speed. But walking upstairs versus jogging upstairs, you feel that difference, and it's because you're having to expend all this work against gravitation in a relatively short period of time if you're running up the stairs. Okay. I also said at some point we'd talk about why kilowatt hour is not a unit of power, and this would be that time. So 1 kilowatt is just 1,000 watts. But let's think about what happens if we take 1 kilowatt and we multiply by 1 hour. The units of that are basically 1,000 watts times 1 hour, but 1 hour is 3,600 seconds, so we have 1,000 watts times 3,600 seconds, which means we have 3.6 times 10 to the 6 watt seconds. Now the fun begins. 1 watt second is equal to 1 kilogram meter squared per second cubed times seconds. We get some cancellation there. We now have units of kilogram meter squared per second squared. So 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules of energy. So kilowatt hour is in fact a measure of energy, and it's quite a lot of energy. So if you're using 10 kilowatt hours a day of energy in your house or your apartment, that is 3.6 times 10 to the 7 joules of energy. That is 36 million joules of energy. It's quite a lot. Ooh, just realized I should have talked about calories in the energy section. So I may need to do an errata video that talks about that. We aren't really doing thermodynamics this semester, so we're not going to use calories as a unit, but yeah, I may need to add something. So I'm going to stop here though, except for one last thing. In the section of Canvas for power, I am going to link to a video on something called the Gossamer Albatross and the Gossamer Albatross and the Gossamer Condor. They are both human-powered aircraft. They were pedaled into flight. It's really kind of cool because if you dig into the information on them, someone like a professional cyclist can output something like 450, 500 watts continuous for a good part of a race. And I think it turned out that these things required something like 350 watts continuous to keep them in the air. And it's neat to know that people can actually manage that. Shoot, now that I'm thinking about it, there is actually one other measure for power that we should at least mention in passing, and that is 1 horsepower. And 1 horsepower is around 735. Thankfully, I have a book right next to me so I can double check. It is, I know I'm at least close. 746. All right, so I'm 11 watts off. Okay, that's a really funny number. How did people come up with it? Well, we're not going to use it because it's an English measure and they're annoying. But the way they actually came up with it was saying, okay, well, I want to sell steam engines. So I want to make horses look bad. How can I do that? Well, a horse can't work all day. Strike number 1. Horses need to rest. Strike number 2. Horses need to get water. Strike number 3. So I'm going to just think about how much average power the horse can output across an entire freaking day. And they came up with this number. Is that the amount of power a horse can output? in short bursts, it can output over 5 horsepower. Human beings, in short bursts, can output over 1 horsepower. So there you go. Horsepower is kind of a misleading unit. That was kind of originally come up with because, hey, I've got this newfangled steam engine and it's painful to make and it's expensive and people don't want them, and how can I make them think they're better than they are? Of course, these days, steam engines are better than horses for a lot of tasks, and internal combustion engines even better than that. So times have changed, but originally this number was they came up with it to make engines look good. Anyway, fun story, but that's all I have to say about that. All right, so we are officially going to stop there. That is the end of power.